Well, this segment will look at calculating the torque on now a full current loop. We know all currents flow around complete closed loops. And if that's in an external magnetic field, then it experiences a torque because of the magnetic field, which we'll show. Um, the calculation is fairly complicated, but fortunately the formulas are very simple, and it's a very simple relationship to apply. And it's very similar to something we've encountered before with electric dipole moments and forces and torques on them in external fields, although more complicated for magnetism. What I want to do is consider a rectangular closed loop of wire that has a total current I flowing around in it in the direction that I've shown. And I want this to be a rigid wire going around it. It probably has many wires, maybe end turns or end wraps, and each one of them might have a current going through it. And if that's the case, then you would take the number of turns times the current going through an individual wire to get multiply those two out to get the total current. But right now, just think of this as the total current that's going around this. And again, it may be wrapped around many times. Moreover, what I want to do is I want to produce a situation where this rigid rectangular circuit, notice it has length L and width W, is free to rotate, but only about the z-axis. In effect, I've got a couple of posts here that will allow the circuit to rotate freely about the z-axis. So it's gimbaled about these two pieces here, but that's the only rotation that this will produce anyway, so we haven't really limited ourselves here in this regard. I've got the origin of my coordinate system sitting at the center of these two gimbal posts, and it's also at the center of the loop. The loop, I've caught it here maybe in a photograph, and remember this is rectangular and it's planar, and so a planar area then has a normal to it, and that's the perpendicular to the plane of this circuit loop is my n hat. And then to define our angles theta, we will have an angle theta here that this n hat makes with the y-axis. Sometimes it's easier to look at it from the top down, and if I look at it from the top down, see if I can get both these pictures in here maybe. Well, maybe not. The magnetic field, if I'm looking at it from the top looking down, I'm looking right down the z-axis, and I'm looking into the xy plane, and that's this xy plane. The magnetic field that I've got drawn up here is all in the y direction, and it's nice and uniform, so it's just b naught in the j hat direction. And these vectors here the picture here allows us to look at this loop from a different perspective. If I have the top portion, it's coming this direction, and I'm really looking at this top here, and then once it gets to the end, it's going to go in the negative z direction, and so the top flows this direction and then goes away from me. It's z is coming out, so the negative z is in, and then it's going to flow back on the bottom. So the bottom is, and if I'm looking down from the top, that's going to be coming right out at me. So that's this one right here, and it flows around in this fashion. I've got this bottom shifted a little bit just so that you can see it, but you have to think of it as right underneath this top portion. And now then, let's calculate the forces on it. The force on just the top piece, well, we know the magnetic force is I L cross B. And so in this case, if I just look at the magnitude, that's going to be the magnitude of I. The magnitude of L vector, well, this is along the top, that's of length L. And the magnitude of B, which is B naught. And now I have to get the sign of the angle between the two. If you look at that, L vector is going in this direction, B is in this direction. So this whole angle over here is the angle that I have to take the sine of. And if you look at that, that's this theta, and then this is a right angle. The normal is perpendicular, so it's at a right angle here. And so it's 90 plus theta. And if I do ILB sine of 90 plus theta, well, 90 plus theta sine is just cosine theta. Bottom is a similar thing. The only thing that's happened is the angle is different. The magnitude is the same. It has the same length. It's going in the opposite direction. So same length L, same B naught. Now the angle now between B, which is in the y direction, and the direction of L vector in this case. So there's L vector going in that direction. Well, if you look at that, this again is a 90 degrees, and so this angle between the direction of B and the direction the current's flowing up there, which is the direction of L vector, is 90 minus theta. But sine of 90 minus theta is cosine theta as well. So both the top and the bottom have the same magnitude. I've got them indicated here. You can use the right-hand rule, but you'll see that the top is coming out of the page at me, and the bottom is going into the page. So they have equal magnitudes. They're going in equal and opposite directions. Usually you set these right at the center of mass of the wire segment. I've got them shifted a little bit here. But the top, by the right-hand rule, is going to be going up, and the bottom going to be going down, and they're equal and opposite, so they cancel out. Similar thing can be seen on the front and the back. Again, the magnetic force is the force on that front segment. It's just I L vector across B. The only difference is if you look at that front segment, the length of the wire here, well, that's W. Yeah? And of course it's going in a different direction. So magnitude is, is the magnitude of I, magnitude of L vector, but that length of that segment was W, times the magnitude of B. And now then it's easier to see in this picture, I is coming out of the page, it's in the Z direction, and B is in the Y direction, and so those are at right angles. And so the angle is 90 degrees, and so it just becomes IWB naught. Same thing for the backside. The backside is on this piece here. So we're looking at the wire, the segment here. That's the back of it, the back of it again. The ILB, the length of wire on the backside is just W. So here, that's W. And so it's IW, B, W is the magnitude of L vector, B. And again, the angle is 90 degrees because current's going into the page and the magnetic field is in the Y direction. So this is perpendicular everywhere to the magnetic field. And so the angle is 90 degrees, and again you get IWB. So if you put all that together, maybe put some unit vectors to it, what you find is this. The top is this expression. The bottom was going in the minus, the front was going in minus I hat. The bottom was minus K hat, and the top, or the back was IWB and the I hat. And all of these cancel out. So one gets sum of the forces is equal to 0. We can do a similar calculation for the torques. I want to get the total torque on it, and it's going to be the torque on the top, the front, the bottom, and the back. I will take the torques. You have to specify the point that you're going to calculate torques about, and I'm going to pick right at the origin. That's going to be the point P to calculate torques about. Torque is in magnitude is the moment arm times the force, and times the sine of the angle between the two. But the moment arm and the force are in the same direction for the top, and so the angle is 0 and the sine of 0 is 0. So same thing for the bottom. The bottom is going straight down. The moment arm is straight down, so they're parallel. and so there's no torques produced by the top or the bottom. That's really by our choice of where we're calculating the torques about. Essentially, uh, the perpendicular moment arm is zero for them. Probably a better way to say it, not r vector equals zero, but that they're parallel or anti-parallel between r vector and the force, and so they are they're collinear, and the anytime you have collinear vectors r vector and f, then their cross product vanishes. The front and back is similar. You can actually compute those pretty simply. It's the in magnitude, it's the moment of the moment arm. That's L over 2. So I'm about the point P. This total length is L, so the moment arm is L over 2. There's the force, and this angle is also theta if you go through and do the geometry. So the magnitude is L naught over 2 times the force that's on the top. Well, the force on the top was on the front, I should say, was IWB naught, and so these become L over 2 IWB naught, and then one for the torque in magnitude has to have the sine of this angle that's between the two here. And again, what you find is that both of these two torques are identical. They remember, a torque in this direction that tends to rotate things about the x-axis, about the z-axis, is considered a positive torque in the z direction, and so both of these are in the z direction, and they both are identical expressions, which we can write like this. I got L over 2, L over 2, so sum those just gets L. It's in the k hat. L times W is just the area enclosed by the circuit loop, and you can take a look at it, but that's the same as n hat crossed into j hat. And now then I've got the following, and a vector is just the area length times width times its perpendicular unit vector. So that's my my a vector. So a vector is by definition the magnetic moment, and those are represented as mu naught. Now well, I've been carrying it as I. It could be n wraps of wire, and so sometimes you'll see this expression. Here we have n wraps of wire, all of which are carrying, any individual wire is carrying a current I, and the area is the area vector of the circuit loop that's enclosed, in our case LWN hat. And that's defined to be the magnetic moment vector of the current loop. And when we use that, this expression here with an n in front of it to extend it to n turns is just the total torque on the loop. It tends to rotate things around so that the magnetic moment aligns with the direction of the magnetic field. So if I release this system in this configuration here, it would tend to rotate around the z-axis until the two are aligned. So this rotates around until it configures in this configuration. And then when mu is parallel to b in the same direction, then the magnitude of the torque is the magnitude of mu, magnitude of b naught times the sine. Well, they're both pointing in the same direction, so the angle is 0, and so that's 0. So these magnetic dipole moments tend to ultimately, if in an external field, point in the same direction as the field. Well, again, a fairly simple expression so long as you know that vector cross product and how to handle that. But the geometry involved is fairly complicated. But nice simple formula.